Hi, my name is Melike Feyza Bahadırlı. I am second year CS student at Bilkent University and today I will present my Physics 1 Autolab project. In this project, it is aimed to observe Faraday's law of induction by measuring the induced EMF in a circular coil of wire. By changing the variables in the equation of Faraday's law of induction, it is investigated how and what variables affect induced EMF. According to Faraday's law of induction, change in magnetic flux creates induced EMF and therefore creates induced currents. Magnetic flux is defined as follows and it depends on the area of the coil and the magnetic field strength. As it's shown here, since induced EMF is defined as the rate of change in magnetic flux, there should be a change in magnetic flux to create induced EMF. In order to change the magnetic flux inside a coil, magnetic field strength, the area of the coil or the time passed can be changed. So, in three parts of the experiment, the effects of each variable in the last equation are investigated by changing the value of one variable and keeping the other variables constant at each time. In the experiment, a magnet is used to create a magnetic field inside the coil, and this magnet is dropped from same distance for each trial to form a constant magnetic field inside the coil and keeping the magnetic field strength as a controlled variable. I dropped a magnet from at the same distance at each time like this. I drop it like this. In the first part of the experiment, the relationship between the radius of coil and the induced EMF is observed. To achieve this, the coils with 2, 2.5, 4, 6 and 8 cm radiuses are used, and the number of turns in each coil remains same as 10 turns. By dropping the magnet through the coil, induced EMF is measured by a multimeter, and the data are obtained as follows. In the Faraday's law of induction equation states that the induced EMF is proportional to the area of the coil, so the relationship between the radius of coil and the induced EMF should be quadratic. As it can be seen, the plot of the induced EMF with respect to the radius of coil plot has a quadratic shape as expected. In the second part of the experiment, the relationship between number of turns and induced EMF is observed. To investigate the relationship, coils with different number of turns are used as 10, 20, 30 and 100, and the radius of coils remains same as 2.5 cm for each trial. By following the same procedure with the first part of the experiment, data are obtained as follows. The Faraday's law of induction equation states that the induced EMF is directly proportional to the number of turns of coil, so the relationship between the number of turns and the induced EMF should be linear. As it can be seen in plot 2, plot has a linear shape as expected. And also, slope of the plot gives us the rate of change of magnetic flux of the coil that has one turn. It is obtained as 0.22 from the plot, and the theoretical value is calculated as 0.28. In the last part of the experiment, to change the time pass, magnet is moved with different speeds. By moving the magnet fast inside the coil, induced EMF increases as expected. And the obtained data are shown here. There are some errors in calculation as it can be seen in tables, and these errors can be caused from some factors. For example, since voltage value that is read from multimeter changes so quickly, the correct value of induced EMF may not be measured properly. Also, there is a cable resistance in crocodile cables, and this causes error rates. Even if magnet is tried to drop from same distance without initial speed, unintentionally some speed could be given to magnet. Also, since the coil is made by hand, there are not perfect circle of coils, and this changes the area of the coils and affect the calculation. Also, when wrapping around the coil with wire, the radius of the coil could be decreased, which could be a reason for the error rates for part 2 of the experiment. Thank you for listening.